This presentation focuses on CO3 intermediate SQL query concept, specifically on how to retrieve and manipulate data from multiple relations using advanced SQL techniques. The topics we will be covering span the full spectrum of intermediate SQL, from aggregation with group by and having to subqueries, null functions, indexes, window functions, and finally complex multi-relation queries. We begin with one of the most fundamental aggregation mechanism in SQL, group by and having. The group by clause groups rows that share the same values in one or more columns into summary rows, essentially collapsing multiple rows into one per group. It is always used alongside aggregate functions such as count, sum, average, min and max. A critical rule to remember here is every column in the select clause that is not inside an aggregate function must appear in the group by clause. Violating this causes an error in most SQL engine. The SQL clause execution order is also important here. It starts from select, from, where, group by, order by. Understanding this order tells us exactly when each clause applies and why certain operations must go in certain places. The example here shows we are counting employees per department and calculating average salary, then ordering by count descending order. It is a classic reporting pattern. Having is often confused with where, but they serve fundamentally different purposes. Where filters individual rows before grouping. Having filters groups after aggregation. This is why aggregation functions like average of or count of can be used in having but not in where. In the SQL execution pipeline, it starts from where, group by, having, select, order by. Here, having sits right after group by, which reflect when it logically applies. The example here demonstrates both. Where first narrows down the employees hired after 2020, then group by aggregates by department, and having further filters to only departments with 5 or more such employees. This is a pattern we will commonly see in business reporting. We now move into one of the most powerful SQL constraints, subqueries, which allow us to embed one query inside another. A subquery is a query enclosed in parentheses within another SQL statement. There are 4 main types. A scalar query is a scalar subquery, returns a single value and can appear in selector where. A row subquery returns a single row and uses row comparators. A table subquery, also called a derived table, returns a result set and is used in the from clause. A correlated subquery references columns from the outer query and re-executes once for each outer row, making it more powerful but also more resource intensive. The example here shows all 3 patterns in practice, comparing a salary to the company average, creating a derived table of department averages, and filtering employees by location using in with the subquery. The in used here is a keyword. Nested subqueries takes this further. We can have subqueries inside subqueries, multiple levels deep. The innermost query executes first and its result is passed upward to the outer query. The key operator used here is nested subqueries are exist or non-exist, any or all, in and not in. The 2-level example on screen finds employees whose department are managed by high earners. A real-world HR used queries that would be very difficult to write without nesting. The exist and all examples show how fine-grained control over set comparison is possible. Next, we address something that trips up even experienced developers, handling null values in SQL. In SQL, null represents missing or unknown data. It is not 0, not an empty string, and cannot be compared using equal or not equal. Instead, we use null and is not null to test for it. SQL also provides dedicated function to handle such as isNull, nullif, and NVL, which is Oracle's equivalent of isNull. The example here shows the practical use, substituting a missing contact with a fallback, adjusting scores by testing 0 as null, and replacing null commission with 0 for payroll. We now move to the performance and data integrity, the domain of indexes and sequences. An index is a database structure that enables faster data retrieval by creating a lookup path on one or more table columns, similar to the index which we use at the back of a book. There are several types of indexes. A unique index enforces no duplicate values. A composite index spans multiple columns and is useful for queries that filter on combination. A cluster index physically reorders the table rows. A non-cluster index maintains a separate structure pointing to the data. A full-text index optimizes searches within large text field. So the main question we arrive here is, when should we use an index? We can use index on columns frequently used in where clauses, join condition, and order by or group by operation. When should we avoid them? We should avoid indexes on small tables or columns that are updated frequently because indexes have a wide overhead. The create index example on screen demonstrates simple, unique, and composite index creation along with the drop index syntax. A sequence is a database object that generates a unique series of numeric values automatically, independent of any table. This makes it ideal for generating primary key values. The key property include a start value, increment step, min value, max value, and a cycle option that determines whether the sequence wraps around after reaching its limit. Oracle and Postgres use next value in index statement directly. MySQL handles this through auto_increment on the column definition itself. Either way, the purpose is the same: reliable, collision-free, unique ID generation. We now look at how SQL retrieves data from multiple related tables using joins. SQL supports 6 primary join types. Inner join returns only the row where there is a match in both tables. Left outer join returns all rows from the left table and matching rows from the right. Unmatched